Okay, we already know from the previous knowledge that uh, light is basically having a two nature, wave nature and particle nature. In the last class, we also see de Broglie waves, and we say that we already found out that even a microscopic or macroscopic, everybody is associated with having a wave. Okay, and he just give it a formula as well, that which is actually this formula. If you just remember that, where is the formula which actually he given? Uh, I think that formula was given as well. What is that thing? This is what the formula is. Lambda is equal to h upon p, where h is the Planck's constant and p was the momentum. All right. So we have gone through this small topic. Now, wave particle duality. So light can behave as a particle and a wave. That's what the theory is. This phenomena is called the wave particle nature of light or wave particle duality. Duality means it will be two wave. I mean, two way, particle as well as wave. Light interact with matter such as electrons as a particle. The evidence for this is provided by the elect photoelectric effect, which is our next topic, technically speaking. So, photoelectric effect, when we will do that, you will find out that actually light interacts with matter such as electrons as a particle rather than the wave, right? So, previously we have gone through young double slit experiment, which shows that light is a wave in nature. Now, there are few things which are very, very important in here. Light as a particle. Einstein said that light can be described as a quanta of energy that behaves as particles, such as photons. Now, when actually once after the photoelectric effect, Einstein is proposing the thing that light are the packets of energy. Previously, it was said it's a wave, it's a particle, whatever they are. But at this point, after photoelectric effect, what he was saying that light, if it's a particle, they're special type of particle, and we can call them quantas of energy, and which are called as photons. Okay? So, photon model of light explains that electromagnetic waves carry energy in discrete packets, and they are called photons. Now, energy of the photons are quantized according to the equation. Now, this is very important thing. Each packet of energy is equal to E is equal to H frequency, where H is the Planck's constant. So basically now what Einstein is proposed or Einstein is proposing regarding the light, that light is actually describes that quantas of energy that behaves as a particle, and he gives them a name called photons. That quanta word, when comes to your mind, remember that this is the basis of quantum physics. Quantum physics is actually started from here. So this is the start of quantum physics, actually, technically speaking. Now, what he said it at this time, that electromagnetic waves carrying energy in discrete packets, and they are called photons. Now, energy of photons can be quantized at E is equal to H frequency. Now, at this point, there are few things which are very, very important, and we will talk about this in a few minutes. In photoelectric effect, now because we didn't study photoelectric effect, so at this point, I'm leaving it here and I'm jumping to photoelectric effect, and after finishing photoelectric effect, I will come back to this. Now, what exactly is photoelectric effect? That's what we are going to do now. And what was it and what was everything? Anyone have any idea what is photoelectric effect? Any one of you?
It's the process of converting electricity into light and vice versa.
That's fine. It's there. Definitely, you're right. But why was it conducting? I mean, why was actually conducted? Because the results were. Now I'll explain it to you. What was that and why it was actually conducting. First of all, remember that when a light shines on a metal, electrons can be ejected from the surface of metal in a phenomenon known as photoelectric effect, right? And sometimes we call this photo emission as well. Now, very interesting fact, which actually comes out of that, and the results which before that, It was just said that particles are, I mean, light is a wave in nature before that. Now, very interesting fact is this is your particle, let's suppose. Okay. So what they were thinking at that time, that let's suppose light when incident on that, that light actually provides enough kinetic energy to the electrons of that material so that these electrons start flowing into the circuit, right? So that type of emission is called as photo emission, and the electrons that are ejected from the metal are called as photoelectrons. In terms of their behavior and their property, photoelectrons are not different from other electrons, and the prefix photo simply tells us the electrons have been ejected from the metal surface by the incident light. That was a normal thing. Everything is the same thing as the previous. The question is, what is the result coming up and what was the predicted, I mean, what was the predicted result at that time, and what are the results which come up, and what was the results actually come up. At that time the theory regarding the light was that light is basically wave in nature. So in this article we will discuss how 19th century physicists attempt to explain the photoelectric effect using classic physics. Now, this is very interesting fact because initial scientists were believing that light is basically a wave. Now, to explain the photoelectric effect in 19th century, the theory was that oscillating electric field of incoming light wave was heating the electrons and causing them to vibrate, eventually freeing them from the metal surface. This hypothesis was based on an assumption that light traveled purely as a wave through space. Now, what actually is the thing? If you just remember a few, I mean, one or two class before, I have told you one thing, that intensity is directly proportional to the amplitude square. Did we do that in the previous questions? I think in the last lecture, I believe.
Yeah, we did.
We did that.
Yeah.
So it means that amplitude is directly proportional to the intensity. And intensity is based on the displacement thing. The big displacement or amplitude means big intensity. Less intensity means less displacement. So what they were thinking at that time, that incoming light was heating the electron and causing them to vibrate and eventually freeing the electrons from the metal surface. Now, very interesting fact is, scientists also believe that energy of a light wave was proportional to the brightness, which is related to the wave amplitude. So basically, more brightness means more intensity. More intensity means more amplitude. That was a thinking of the scientists of that era. In order to test their hypothesis, they performed an experiment to look at the effect of light amplitude and frequency on the rate of electron ejection as well as kinetic energy of the photoelectron. Now, remember that there are two different things. Rate of electron ejection means more current, and kinetic energy of the photoelectrons is different. Now, based on the classic description of light as a wave, they made the following prediction. Now, you tell me one thing. Kinetic energy of the emitted photon should increase with the light amplitude or with the frequency? More intensity. More intensity means more kinetic energy. More kinetic energy means kinetic energy of the electrons increases. Remember that. What they believing at that time is that amplitude is everything to do with the intensity, or in other words, amplitude is everything to do with the kinetic energy of the photoelectrons. They were believing at that time. And second thing is, what is the second prediction? Rate of electron emission, which is proportional to the electric current, should increase as the light frequency is increased. Because they think that waves are the one having different frequencies. So if they think of that time, If we increase the frequency, the more and more electron will get more and more kinetic energy, or in other words, more electron will flow. So if you increase the frequency, technically speaking, current in the circuit increases, or photoelectrons in the circuit increases. If you increase the displacement, kinetic energy of the electrons increases. Till now, everybody's clear?
Yes.
Okay.
Yes.
Yes. What
Yeah.
about you? Okay. So that was a classic physics description. For that reason, technically speaking, that photoelectric effect experiment were being conducted at that time. They wanted to see that result. When result came in, it was totally reversed. Kinetic energy actually wasn't increasing due to the increase of amplitude, but due to the increase of frequency. And rate of emission is actually proportional to the increase in the uh, what do you call it, amplitude thing. Totally reversed. That was a big confusion at that time. So what happened? To help us understand why they made these prediction, we can compare a light wave to water wave. Imagine now they give you a small description why that thing they actually believe in. We can compare a light wave to a water wave. Imagine some beach ball sitting on the docks that extends out into the ocean. The dock represent a metal surface, the beach ball represent electrons, and the ocean wave represent the light wave. Now, this is very interesting. The dock represent a metal surface. Now check this out. Why they made this? If the amplitude of the wave is high, right? What happened? Low amplitude, these balls will go a bit higher. So low kinetic energy. Because amplitude doesn't give them that much velocity so that they will run. But higher amplitude, they will go higher, so higher kinetic energy. That's what their belief is. Understood? Hello?
Yes.
That is, I'm
Yeah.
talking
So
about a, yeah, that is, I'm talking about the classic physics for the time being. Remember that. If a single large wave were to shake the docks, we should expect energy from the big wave would send the beach balls flying off. So this also was physicists believe would happen if the light intensity was increased. Light amplitude was expected to proportional to the light energy. So higher amplitude light was predicted to result in photoelectrons with more kinetic energy. So it means that if you want to give more kinetic energy, more amplitude of the wave needs to be provided. And if you really want your dot to be removed, you need very high frequency wave that can remove this. Now, this same thinking they took it with them during the photoelectric effect concept, right? So what they believe is light amplitude was expected to proportional to the light energy. So higher amplitude light was predicted to result in photoelectrons with more kinetic energy. Classic physicists also predict that increase the frequency of a light wave at a constant amplitude would increase the rate of electron being ejected, or in other words, current will be increasing, right? Using our beach ball analogy, we would expect wave hitting the dock more frequently would result in more beach balls being knocked off, and the dock compare to the same size wave hitting the dock less often. Now that we know what physicists would happen, let's look at what they actually see the results. Now, once again, quickly, when they actually do this effect or photoelectric effect, they actually fall a specific monochromatic light on a metal, right? And they were believing that if the amplitude of that particular wavelength is increasing, technically the kinetic energy of the electron increasing. And if the frequency is increasing, or you can change different light here, then it actually increases your flow of electron, right? Now, what was the result? Let's see that. When results were performed to look at the effect of light, amplitude, and frequency, the following results were observed. The kinetic energy of photoelectron increases with the light frequency rather than amplitude. And electric current remained constant as the light frequency increased. So basically, when they change different lights, they have seen that, technically speaking, it's the kinetic energy that is increasing, not the current. Current remains the constant. But when electric current, they actually increase the amplitude, that increases the electric current rather than the electric energy. So kinetic energy of photoelectron remain constant as light amplitude increases. Now these results were completely at odds with the predictions based on the classics description of the light as a wave. Now do you understand what exactly happens? Again, I will revise, I will repeat it because that's a new thing for you. Initially, what scientists were predicted at, because they wanted to explain the whole photoelectric effect with the classic physics, and they were thinking at that time that light was a wave. So they were thinking that if the wavelength amplitude increases, the kinetic energy of the electrons are increasing. If frequency of the wave increasing, then basically current in the circuit or photoelectrons start flowing more often. So more current increasing. That's how they explained or they predicted the results by using photoelectric effect. But when the results came in, they were totally opposite of what they were thinking. What they have seen that kinetic energy of the photoelectron increase with the frequency rather than with the amplitude. And at that time, they keep the frequency constant. Then they have seen that kinetic energy of photons remain constant as light amplitude increases. So initially, the current will be constant and kinetic energy will increase if we increase the light frequency. So frequency is directly proportional to the kinetic energy and current is directly proportional to the amplitude increase. Now, how to explain that? Because this is not the wave of light, I mean, light as a wave anymore. So, for that, now at that time, our founder of the modern physics came in, and he is the one and only Albert Einstein. At this time, he proposed that technically speaking, light is not a wave, light is not a particle, but they are the packets of energy where each packet is having quantas into this. And that quantas of energy are called as photons. Now he said it, the energy of photon can be calculated by using the Planck's constant. E is equal to HF. This is the energy HF. Now you can see that if frequency increases, energy increases as per the results. That is how he proved it. Where E photon is the energy of photons in joules, and this H is a Planck's constant. And it has a value as well. Let me show you the value. What was the value? Let's see. According to the Planck's equation, the energy of photon is proportional to the frequency of light, and the amplitude of light is then proportional to the number of photons with a given frequency. All right. So, concept, as the wavelength of photon increasing, what happened to the photon energy? What happened to the photon energy? Let's see that. According to
It
the
decreases.
Planck's, yeah, you're saying something?
I think it decreases.
No, that's what the point is. It's everything to do with frequency rather than wavelength anymore. As the wavelength of a photon increasing, what happened to the photon energy? With energy, it has nothing to do. With frequency, it has to do. But let's see. Let's see. So according to the Planck's constant, the energy of photon is proportional to the frequency. E is equal to hf. So the light frequency f is inversely proportional to the wavelength. So c is the speed of light. Lambda is the wavelength and f is the frequency, right? So basically, in such case, when c is the speed of light, this means that increase the wavelength, decrease the light frequency. Therefore, as the wavelength of photon increases, its energy decreases. So who told for a minute before that actually increase in wavelength, decrease the energy? I think Zoha, you told it. Who
Yeah,
said? So you were right.
I did.
So if frequency increases, energy increases. If wavelength increases, energy reduces. Any question till now in photoelectric effect? Because this will go long. Any one of you?
No. No.
Yes, Manur, Zoha,
No.
Manur, you?
So I understood the beach ball example because that makes sense. Why does frequency increase the kinetic energy?
Yeah. Now, because actually it's not like, you know, how they actually checked it. They actually use different lights. Because, you know, as I told you previously, and as per our previous knowledge, I'm talking about IGCSE knowledge, we know that frequency never changes. It's a constant quantity. What we have done, we have used different light source, monochromatic lights, and then we checked it, and then we found out that actually frequency increases, energy increases, but the current remains the same. So that's the point actually. Once we do this experiment, the results are totally reversed. That's what the point is. What we were expecting were different, but the results that came in were totally different. So definitely there is something wrong with our concept of light as a wave. So at that time, Einstein came in and he said, okay, no problem. It means that if the energy of photon is something to do with frequency, then the formula is E is equal to H frequency. So he gave it a formula. Planck actually gave a formula E is equal to H frequency. He said the energy of a photon is equal to H frequency, right? That's the results. I'm not talking about general. That's the result of a photoelectric effect. On the basis of that, Einstein actually proposed that model. All right.
Yes.
Okay. Now, once he reached to the, you know, the core of that, now what he did, he used different light sources, red, blue, green. That's the reason they give different colors. So we can think of incident light as a stream of photons with energy determine the light frequency. When a photon hits the metal surface, the photon energy is absorbed by the electrons in the metal, and the graphical below illustrate the relationship between the light frequency and the kinetic energy of the ejected electrons. Now, why the different light sources are shown? Each light source provides a different energy to the electrons. So, kinetic energy of the ejected electron will be different for different light source. For red light source, it will be different. For green light source, it will be different. For blue light source, it will be different. Right? Now, at this point, there will be a new concept coming up. Check it out. The scientists observed that if the incident light had a frequency less than a minimum frequency, mu naught, then no electrons were ejected regardless of the light amplitude. Now, this is interesting. When they use red light source, might be possible in a some metal, no electrons getting the extra kinetic energy so that it will actually knocked out from the surface. Now, we are trying to knock out the surface, we are trying to knock that different electrons from the surface of the metals by giving different frequencies. Let's suppose, I'm just giving you an example now. Let's suppose I'm using a light having 50 hertz frequency. Let's take it example. When I apply this light source, definitely this light source, when we provide them, kinetic energy of the electrons also increases. I'm talking about the electrons in the metal, and but they are not good enough to actually knocked out from the surface of the metal, regardless of if we increase the amplitude of the electrons. But we are not talking about amplitude anymore. I'm talking about the frequency. So you can say that 50 hertz of frequency is not providing enough energy or kinetic energy to the electron, so they will have more enough energy to actually knocked out from the metal. Let's increase this 50 to 60, let's suppose. Still, kinetic energy which is provided to the electrons are not enough to actually knocked out from the surface. As soon as I provide 70 hertz, what I have seen that at constant amplitude, electrons are start moving into the circuits in the form of electricity. Then what did I see? I see at 70 why this thing happens. I start reducing the frequency. Let's suppose I have reduced it to 61. When I apply 61, what I have seen that I have seen a small amount of current. Now my point is at 60 hertz, there was no current. At 61 hertz, there was a current. What does it mean? That extra 1 hertz is the frequency that caused that electron to actually eject it from the metal surface. Am I right? Hello?
Yeah.
So am I right that this 1 hertz of the frequency is the one which is actually a cause of electron to eject from the metal?
Yes.
So my question is, can I say that 61 hertz of the frequency is the minimum frequency required to actually start ejecting the electron from the surface of that metal I am using? Can I say that?
Yeah, but is that actually true?
No, no, of
Viewer?
course, that's what I'm saying. For the time being, just listen to me what I'm saying. It means that before 61, whatever frequency I'm providing, it's none of use because I will not get any photo electrons, or in other words, there is no electron flow in the circuit. As soon as I reach to 61 hertz, electrons start flowing, but very minimum. Now, if I increase my frequency, more and more electrons are increasing because kinetic energy increases. When kinetic energy increases, electron flow increases. Or you can say at least kinetic energy of the electron increases. So that minimum amount of frequency that actually allows electron to start flowing into the circuit, we call that energy as threshold energy or threshold frequency. There is this energy is called as threshold frequency. So what is the threshold frequency? That is a minimum frequency required to knock out the electrons from the metal surface. Now, if you increase the frequency more than the threshold frequency, electron would be ejected from the metal. For every single metal, there must be a threshold frequency requirement. If you apply more than that, then and only then you will have electron ejected from the metal, or you will have a photoelectrons flowing into the circuit, or in other words, you will have a photo electricity or photocurrents. Otherwise, no current is flown. So at this point, we actually came across a new term that is called as threshold frequency. It means that every single metal has a threshold energy. Some metals have a less threshold energy. Some metals have a very higher threshold energy. Now, one of my question is to you is, what if a threshold frequency is zero for some metal? What does it mean?
Um,
It means that it's very easy to knock out the electron from that metal. You just drop any frequency and you will have a current in the circuit. That's
Is
what
there
it.
anything like that?
We have a metal, actually, we have different metals whose threshold frequency will be very less, but definitely not zero. I'm just giving you a hypothesis that if frequency is zero, it means in a general condition, in at room temperature, you will see electron flowing if you have a proper wire and all the circuit as we have in photoelectric effect. Now, if you check this out, that the graph which is shown here, that graph is between the light frequency and electron kinetic energy. Did you notice that at first initial period, like till this period, no energy is increased? But as soon as you increase or you reach to the frequency equal to the threshold frequency, suddenly the kinetic energy now increasing, increasing, and increasing. If you increase the frequency more than the threshold energy, I mean threshold frequency, the kinetic energy will be more and more and more and more and more. So the frequency, now we actually came to find that result, that if the frequency we have to apply to get the results or to see the current, the minimum requirement is that your frequency at which you are playing with or at which you are performing that experiment, that frequency should be at least equal to the threshold frequency of that metal. If it's less than the threshold energy, threshold frequency of that metal at which the electron may be ejected, you will not see any photoelectrons flowing into the circuit. All right, understood?
Yes.
On the other side, let's see the graph between light frequency and electron current. Now, if you check this out, you will see a straight line. Remember that if your frequency is greater than frequency V naught, then you see a constant amount of current. But there must be a current, right? How can you increase that current? To increase that current, you have to increase the displacement, or in other words, you have to increase the amplitude. Then and only then you may get this type of curve. Otherwise, you will have a constant flow of current. But electron kinetic energy will be more and more if the frequency of the wave or frequency of the light which you are using is increasing. All right? Understood?
Yeah.
Or any question?
Hmm.
So for frequency greater than, remember this sign is also a sign of a frequency. Sometimes it's written as F naught, sometimes it's written as mu naught. Depending upon whatever sign comes to you, you should know that this is a sign of frequency. So what they're saying is, for frequency greater than frequency naught, electrons would be ejected from the metal. Furthermore, the kinetic energy of the photoelectrons was proportional to the light frequency. The relationship between photoelectrons' kinetic energy and light frequency is shown in the graph. Till here, everything understood? Or any questions?
Till here, it's okay.
It's okay. So, what have we found out at this point till here? That our kinetic energy is everything to do with the frequency. But that frequency should have a minimum value. That minimum value would be called as threshold frequency. That threshold energy will be the minimum frequency required to knock out the electrons from a metal. So it means that every metal should have a minimum frequency requirement at which electrons start knocking out from that metal. That frequency is called as minimum frequency. And minimum frequency is called as threshold frequency.
Hmm.
All right.
Yeah.
Okay, now let's move further in this. There is a equation of photoelectric effect, and because the light amplitude was kept constant, as the light frequency increases, the number of photons being absorbed by the metal remain constant. Now this is interesting because we are trying to find out the relationship between the frequency and the energy. So we are keeping the what you call amplitude constant, right? So amplitude is constant. It means the rate at which the electrons were ejected from the metal remain constant. Or in other words, the flow of electrons or the current remain constant. The current is not increasing nor reducing. So relationship between electron current and the light frequency is just a straight line or a horizontal line. All right?
Mm,
Understood, everyone?
yeah.
Now, at this point, let's
Yeah.
quickly summarize once again from which point we have started our work. Yes, Mahnoor, what was the prediction before we start the photoelectric effect when they are trying to explain or they are trying to predict the result of photoelectric effect by using the wave theory?
That amplitudes increase the kinetic energy.
Yes. Okay. And what about the frequency?
It has no effect.
Now, frequency, if you increase the frequency, then amount of current increases, photoelectrons increasing in the circuit, right? So basically, they are predicted two results. One is the amplitude. By increasing amplitude, they were thinking the kinetic energy of the uh, electron increasing. And if you want to increase the current, then you should increase the frequency, or you can use different frequency with the higher frequencies one. Then it will increase the current in the circuit, or it will increase the current in the circuit or photoelectrons in the circuit, right? That's what they are believing through the wave theory. But when the results come, Alicia, what was the result coming up? What were the results of photoelectric effect that actually made them confused? Or Zoha, you?
Um, they found that increasing the amplitude did nothing.
No, increasing the
Uh,
amplitude did increase the number of electron flow, or you can say current start increasing. But by increasing the frequency, that increases the kinetic energy of the electrons of that metal. Understood? So,
yes.
in other words, you can say that at a specific frequency, the current flow is constant, right? But the kinetic energy will be increasing, or kinetic energy will be increasing or decreasing at the base. I mean, it will be having a directly relationship with the kinetic energy of the what you call kinetic energy of kinetic energy of the electrons. The frequency has a direct relationship. Alicia, what is meant by threshold frequency?
Like the minimum frequency required
For what?
for the electrons to release.
Yes, the minimum you can say frequency required to knock out the electrons from a metal is called as from a particular metal is called as threshold frequency. It means that once you are using once you are performing this this experiment, you should know the threshold energy or threshold what you call threshold frequency of that metal as well, that this particular frequency is required to actually knock out the electrons from that metal, so that you at least use that particular frequency light. Otherwise, you may not see any results or any current actually using that particular frequency of the light. Understand?
Yes.
Now let's proceed further. What are the actual results where what they actually achieved by using Einstein equation? Now at this point, you can see this equation now. This is very interesting equation, mathematical equation. Now, my point is, what is this equation? Let's see. This is called a mathematical equation. Now, what exactly is mathematical equation? We can analyze that the frequency relationship using the law of conservation of energy. The total energy of incoming photon, E photon, must be equal to the kinetic energy of the ejected electrons, K electron, plus the energy required to eject the electron from the metals. Now, this is very interesting fact. Now, Einstein gave an equation. Now, what is this equation? Let's see. He said the energy which is providing by the photon, he divided that photon energy is divided into two things. One energy is definitely this sign, which is like that. That, you know, that frequency we were talking about, minimum requirement to knock out the electrons from the metal. This phi is called as work function. And this can be given as E is equal to HF. In other words, work function is the minimum energy required to knock out the electrons from the given metal. On the basis of, now, what will be the formula for the work function? E is equal to HF naught. F naught will be the threshold frequency. So you can say phi means work function and work function means a threshold energy, the minimum energy which is required to knock out the electrons from the given metal. All right. So like the threshold frequency F naught, the value of phi also changes depending on the metal. We can now rewrite the equation of photon in terms of light frequency using Planck's constant. So basically, photon energy can be given by, I just told you the phi energy, it wasn't a phi energy, it's a photon energy. This is equal to HF, which is equal to kinetic energy of electrons plus phi. Again, what is phi? Phi is the minimum energy required to actually knock out the electrons. Once the electrons start knocking off, then they must have a kinetic energy with them as well. So these two energy will add to give you the energy of the photon. If your photon energy is less than that combination, then that energy will be unable to knock out the electrons from the metal, or at least that HF should be equal to the work function. So what I have told you that phi, what is the minimum requirement? I was talking about the minimum requirement, that is phi must be equal to HF now. Because this condition will only fulfill then and only then at least electron will be ready to knock off. If you increase the frequency from there F naught to some point value, then definitely you will get that kinetic energy of the electron. Otherwise, you will not have any kinetic energy of the electrons. So rearrange the equation, you will get this. Kinetic energy is equal to H frequency minus the work function. This phi means the work function. So basically, we can see that kinetic energy of the photoelectrons increasing linearly with the frequency as long as photon energy is greater than the work function. So photon energy should be greater than the work function, which is exactly the relationship shown in the graph. We can also use this equation to find the photoelectron velocity, which is related to kinetic energy as follows. Now, this is the formula. Now, we have seen the formula kinetic energy of the electron equal to HF minus phi. Now, we can say that kinetic energy of the electron is equal to 1 by 2 mass of electron V square is equal to H frequency minus work. Did you see how I changed the equation from the standard form to a proper written equation, which is now we have a kinetic energy as well on the left hand side, 1 by 2 MeV square is equal to HF minus the phi. Where mass of electron is also there, Me is equal to the mass of electron, V will be the velocity, H will be the Planck's constant, and F will be the frequency. Any question till now?
No.
See, I'm trying my level best so that you understand this photoelectric effect. This is a full detailed topic, and our whole class will be totally based on photoelectric effect main theory, right? So now, once we reach to this equation, now check this out. If you increase the amplitude, right, the current will increase. Did you see that? That straight line coming from the origin that we didn't talk about previously. So technically speaking, at this point, if you increase the amplitude, you will get more and more and more electron. But at that time, frequency will be taken as constant. But whatever frequency you should take, you should keep in mind that frequency value should be greater than the threshold frequency. Otherwise, you will not have any current in this. So in terms of photons, higher amplitude light means more photon hitting the metal surface. This results in more electron ejected over a given time period, as long as light frequency is greater than the threshold frequency. Increasing the amplitude will cause electron current to increase proportional as shown. Now, if you check this out, here, amplitude will not change the kinetic energy again as far as your frequency is greater than the threshold frequency. All right, any questions?
No.
So everything is done in photoelectric effect. This is what the last result we have is. So we actually found out the equation for the work function and everything. So what this said is, since increasing the light amplitude has no effect on the energy of the incoming photon, the photoelectric or photoelectron kinetic energy remain constant as the light amplitude is increased. If we try to explain this result using our dock and beach ball analogy, the relationship in the graph indicates that no matter the height of a wave hitting the dock, whether it's a tiny swell or a huge tsunami, the individual ball would be launched off the dock with the exact same speed. Thus, our intuition and analogy don't do a very good job of explaining these particular experiment. So this is what the photoelectric effect was. All right. So did you understand everything in photoelectric
Yeah.
effect? So what was the
Yes.
conclusion? Conclusion were very interesting. The equation we have came across was E photons, that is equal to photons energy or Ke of photons plus the work function. So we know that E photon will be equal to HF, and kinetic energy of the photons will be equal to, not photons, sorry, for electrons will be equal to 1 by 2 MeV square plus phi. So technically speaking, the phi value will be equal to HF minus 1 upon 2 MeV square. This is the formula to find out the minimum energy required to knock out the energy from the metal. All right.
All right.
Anybody have any question, please ask, because this is very, very important topic. Your whole, what do you call that, quantum mechanism is based on this. Because if you understand that, then furthermore, you will understand everything. Because from now onwards, you will be treating that light as a photon rather than you will be treating it as a wave. All the further, topics related to, that hadron and so many things, nuclear fission and fusion reactions, and that components, that what you call that pair production and pair annihilation. You are taking that light as a photon, but not as a wave. That's the reason. This is the basis of that. Now we are actually thinking of light as a photon rather than we are believing that light may be an object, or maybe you can say it's a wave. It's no more a wave, no more an object, but we are considering it as a photons or packets of energy. Right?
Right.
Okay. So now I'm finishing the class here, but I will upload that lecture on the up, I mean, on my drive, and you can ask our coordinator to give it to you. I better ask you to go through that lecture once again, listen to me, because it was a full theoretical lecture which I have delivered. See the diagram which is given to here, that diagram which actually shown that photons are bombarded on the metal, and then as a result, you will get the current. In the next class, I will show you the small circuit related to that, but that is the main concept which actually I have given today. Okay, so I want you to go
Sure.
through that lecture and see through or listen to that lecture. All right.
Sir,
Yes.
you still haven't told us what is the value of Planck's constant.
Yeah, I will tell you. Don't worry. When the numericals will come, I will give you the Planck's constant value. Remember that that value will be provided to you. It's a very long value, 6.66 10 raised to power something. If you really want to see that, I myself don't remember that. So I will show it to you. It's here. Here. Is it here or not? Okay.
6.626. Okay.
This is the
Times
Planck.
10. Huh?
10 raised to power minus
Yeah.
34 joules per second. So the value is actually provided to you in the your separate sheet. So don't worry about the values. The important thing is that you should know the concept behind it. The constants values are normally provided in the paper, I believe.
Okay.
All right. So see you in the next class tomorrow. And then we have one class on Sunday as well, right? At 4 p.m. Pakistan time.
Yes.
Okay, then. See you tomorrow then.